Next one will be Mr. Tuccari from INF IRA and MPIFR on how artificial intelligence meets radio astronomy.
Thank you very much. I'm going to talk to you about something strange even to me, application of the artificial intelligence in our field, in the radio astronomy field. I started to consider this option for more reasons. First of all, because we are, how to say, just having around many applications of this type. And then that was just joined with a definition of new projects. So it was a sort of a natural way to consider such a kind of utility, like a possible application. So let me shortly mention some sort of obvious concept. As I said, the artificial intelligence is nowadays involving any activity, any aspect of our life. Sometimes this is evident, sometimes it's not that evident, but it's a little bit more inside the things. What can we say? That the technology is nowadays ready to have even such scientific applications, scientific aspects joined with the artificial intelligence. So now we can have available some platforms which can be software in the beginning for developing solutions of this type. But let me say something more. What is such artificial intelligence? Okay, it's a science. It's also for its own. It's a science and technology, having the aim to make machines in some way intelligent. Intelligence, it's a definition of intelligence for a machine. Of course, it's restricted. But what we would like to see, it's a machine able to learn and solve problems. I think this is an acceptable definition. In terms of science of engineering, but who is studying or which type of science or technology is studying artificial intelligence? It's a very particular, very precise branch of computer science with such aim, as you said, just to build machines able to help us to solve problems and maybe better than us, maybe not, depending on the problem and depending on how good we are to make these machines. Short story, very short history about that. The very technological first light of the artificial intelligence is, of course, the creation, the realization of computers, digital computers. But there was a date, a very precise date, when it was defined, was coined the name artificial intelligence. That is, that was in this Dartmouth Summer Research School. I mean, it was a meeting, not a school, it was a meeting, which was then defined also like a project, where during the summer, there was a brainstorming activity in such university. And at that point, under the Shannon suggestion, was defined such term which today we widely use. So later, there was a sort of gap, not too many developments during the 60s or 70s, but that came back again in the 80s, when was defined, were defined algorithms and applications making use of such methods. Then it was just a continuous flow in the 90s and so on. You can see as it was defined with more precise goals like learning, application with the speech recognition and so on, driving machines, which have been seen in the latest period. Where it's used today? Today it's used in many thousands of applications. Any industry, I would say any, most of the industries are using such technology. Of course, in specific, in the computer science, we have dedicated parts which make use of artificial intelligence, which are object-oriented programming, graphical user interface, and so on. I mean, things that you probably know. The storage management, maybe that's an interesting part of this application, and so on. You can see here some examples in telecommunication, in aviation, air traffic controllers. I think I have seen for the first time this kind of application in the San Francisco airports. I would say more than 10 years ago, probably almost 20 years ago, and so on. Robotics, all the, for example, cars industries are using for welding robots, which are able to make such to use this ability. And of course, many other examples are possible for and are implemented for everyday life. So it's obvious that we can ask ourselves, but can we use, are those methods you already used? And yes, I would say yes, because we have many groups around the world which are trying to implement or already using AI applications for example, the easiest, more diffused probably is the classification of radio objects. That's one way to help astronomers to make classification, pulsar detections. Even it is used also, it is going to be used for controlling a complex network of telescopes, where it's difficult, when it's actually complicated to manage more aspects and more parameters in a complex network. In RFI mitigation, we can see such sort of application on data which have been collected mostly. I mean, inside the existing database of data. Fast radio burst detection, it was mentioned already, that is another kind of application. And or radio anomaly detection, and it's easy to think about SETI in this case. So, and I suppose that more and more will come with the time. The initial aspect, this was initially applied making use of particular languages like Prolog or another one, Lisp maybe, something very, very old types of languages. Well, but in practice, what we can make use today, what can be useful for us today would be more than adopting software methods to be able to operate in real time during time acquisition, during our collection of data. That would be a much better solution if we have methods or we can do something like this. So it's more attractive that way to be able to develop methods and use hardware, or possibly something mixing hardware and software for such applications. Then having in mind this sort of background of existing possibilities, because work, in my group, we work with two types of applications. I would like to give you two examples. I cannot provide the results because I don't have results, but we already are working on such applications. I think we started in the beginning, just before the pandemic, the beginning of the pandemic. We started to define and work on that. So I don't have results to show you. I hope to be able to present results at the 8th BAASP in 2023, possibly, hopefully. But now I think it's interesting, if you agree with me, that to understand what we are doing, what we plan to do, and how we are going to do, because more than what we are going to do, is interesting to define a method which can be applied in other situations. So I have a first example. First example is applied to a antenna array. Okay, we work even with a small antenna array on the Etna volcano, which is working in a broad range, but it's mainly focused for 327 megahertz observations. The purpose is to have a sort of sensor for VLBI at low frequency. It's a study. It was financed by AtLab, which is producing DVB-C systems. Of course, when you operate in low frequency, nowadays I have to say that at any frequency is a problem, but in particular, when you operate at low frequency, you have many problems with RFI. So we asked ourselves, but how could we minimize contribution of RFI for low frequency observations? And so we try to understand whether a deep neural network could be used for such purpose. Very shortly, because time is running. So Antar is a bidimensional antenna array. And the beam, which is to be created by the contribution of the different antennas, combining amplitude and phase of them, as this is done normally in any antenna array. So the point is that if we are able to know in real time the worst case contribution, the worst case RFI directions, where are they coming from, in which direction, maybe we can trying to optimize the beam creation, placing minimum in the side lobes in the direction of the worst case RFI. This is maybe easy to be done when you have all the data on your desk, but when you want to do in real time, you need to do something different. You need to have some more help. And the neural network, maybe it's a possibility to do. But this has to operate in real time. So as you know, as you probably know, any neural network requires training. So we are making use of software platform using a couple of GPUs, very high-end GPUs, able to test and different types of commercial neural networks, because you have libraries already available, but with a training which is actually performed using real interference and a small drone which you can place on the sky in fixed positions with a small transmitter in the range you want to observe. So making a collection of those, you can create a model which can then be later uploaded on a machine, on a hardware machine, making use of system-on-chip devices. So a combination of FPGAs and processors, which can be able to make the operations in real time. Many words, but maybe with a picture you can see much better. So we have a detector which can find the direction of the worst case interference. But you have also a direction of the source you want to observe. So when you have trained a number with a number of source positions, a number of worst case radio interference, you can create an optimized beam with the minimum pointing on the worst case RFI. So this trained network, which was done in software, is then loaded in a hardware network, which is able to operate in real time. I can tell you that from that point of view, we have some results because we have been able to make some observations, some training on that, but I didn't include here because it's not a final version. I didn't want to present today. So the second example, if I have other 3 minutes, is to the DBBC4. DBBC4 is a new backend, which it's a new project, which we hopefully would like to start next year and will last 4 years. And where this artificial intelligence is strongly applied, there are hardware modules making use of inside the DBBC4 project. Here is a short description of the DBBC4. Maybe you can see very quickly. What I would like to point out in the DBBC4 is that, of course, it's a continuation of DBBC2 and DBBC3, so it's a sort of it's an evolution. And what is more important, it's behaving 8 IFs with such bandwidth, plus 8 4 gigahertz bandwidth. So it's the total. In a full system like this, you have a bandwidth of full bandwidth of aggregate bandwidth of 256 gigahertz, and you have here you have a plot with evolution of the DBBC family from the first to this fourth in terms of input bandwidth and data rate. But again, I would like to point the question that there is a controller with the AI applications, and in this case, the first we plan to have many applications making use of such technology. But the first one we are trying is one which would like to mitigate the interference contribution. How? In a simple way. When we have a presence of periodic RFI or just pulses, not periodic, impulsive, but not continuous, then we can have a choice. We can have a chance to make something to improve the signal to noise ratio. Indeed, it was demonstrated that when you replace the interference with noise, completely independent noise, so not correlated noise, but you replace such large or maybe not that large information with the noise, simple noise, similar to the noise you are observing, the signal to noise ratio, it's improved. So our idea was at that point to find a way with the network to detect when you are in such, if you activate this mode, when you could be able to detect when an RFI is present in your data for more reasons. But this is demanded to the network you train it in such sense. Then you can trigger the introduction, the replacement of data, and the replacement of data can be done in 2 ways. One is with the scrambled data. Scrambled means that you can descramble later when you are in playback situation, when you read back the data, or when in the worst case, when it's really very bad, then you can just put pseudo-random noise. Again, it was made a similar type of consideration we already said earlier, a similar type of campaign which can be made, was not made, of course, can be made in the same way. training with real-time RFI. And then such network is planned to be inserted in a hardware piece, again, based on system-on-chip devices, which are very powerful now for synthesizing network mostly in hardware, like FPGA, and for those parts which cannot be synthesized with the fast, in some way, fast processors. Okay. Here, the similar object. So training in that case will be made simulating what is could come like a periodic or pulses, not periodic RFI contribution. Okay, thanks. That was the last.
Okay, thank you, Gino, for your presentation. We have a comment from Paco Kelmer. So, would you want to ask your question
yes.
in voice? Yeah, please go ahead.
Hi, Gino. I had heard
Paco.
Digital BBC4, and it looks like a really exciting project. Now, my question is very practical. Who are the clients of this device? I mean, I see that you mentioned IBS, EVN, even EHT. But these networks are not in need, I think, of input of 256 gigahertz. So
Well, Paco, yeah, I think your question helps because you see, I don't know if it is, you see, the input bandwidth is up to 8 times that, plus 8 times 4. I mean, like any DBBC 2 or 3, you can also have a smaller object. The maximum, because it's possible, simply because it's possible. For example, we see in this moment that there is a good interest from the new generation EHT. We have a dialogue with them, maybe not for the full system, but for a good part of this system. So the point is that this is possible to be done. And so when this is possible, you can define the maximum, and then any type of observation could just decide how many of such modules you need to be inserted inside one box or not. I think it's a choice.
Okay, thanks to you.
Welcome.
The question from my side. Thanks again, Gino, for very interesting and, as usual, very intriguing talk, because very unknown in this case. But a question, so this DBBC4 up to 28 gigahertz, but you are targeted it for low frequency antennas. Is it means we can organize multiple beams, and beam number can be hundreds to cover all sky in this case, and process with DBBC4?
It's not targeted for low frequency. This is target for that range, and that was you can see that there are ranges up to 4 gigahertz, which can be the IF or the RF of many receivers we use normally in EVN, for example, or on IVS. Then the bandwidth 28 gigahertz is, for example, fully covering the IVS band, which is 14 gigahertz, and then can cover even K band in a single shot, similar to Brand. Brand receiver is also from up to 15.5 gigahertz, from 1.5 to 15.5. So it's a broad range which can be used in. Another application, I suppose, can be for these millimeter 3-band receivers.
Yes, clear. And second question, so you have IE system which is make classification or of RFI signals, right? So you try to find them and cut them off. But in this case, we can also find something unusual or unclassified signals coming from sky, which are not in a normal way. We just throw away these signals, and by your system we can catch them. Is it right?
That's the goal. That's the goal. We started to study with the easy, in some way it's not easy, but the easiest solution, which is for RFI, not continuous RFI. I mean, something periodic, which can be, in some way, it's not that difficult to be detected, but it's because it's very variable. So you cannot make a plan for that. You need a sort of machine like this to understand when it's coming, if it's coming, and things like this, and to help the system to mitigate the efforts. But yes, the other goal is just to detect unusual, how to say, not expected noise as the one we normally in continuum are searching and recording.
Okay, thank you for the questions, and thank you, Gino, for your presentation.